The ASHRAE Integrated Sustainable Building Design Competition challenges students to optimize the design of a proposed building to exceed the requirements of ASHRAE's Green Standard, Standard 189.1. The 2017 competition focuses on a meteorological center building on the Diego Ramirez Islands, a small archipelago off Chile's southern coast. The Catholic University of America student team rose to the challenges of this unique site by engaging in a truly integrated design process and exploring innovative design strategies. The following animation outlines the major sustainable building strategies and synergies applied to the building. Further details will follow. The new building is located on Isla Gonzalo, the only inhabited island of the Diego Ramirez Islands. It is located in ASHRAE Climate Zone 6A, cold humid. There is very little variation in the mean temperature throughout the year, and solar radiation levels are low. Cold, strong winds cross the site year-round, coming mostly from the northwest. Heating degree days greatly outnumber cooling degree days on the site. Therefore, the team sought to maximize both internal and external heat gains. The Diego Ramirez Islands are breeding grounds for many sensitive and endangered birds, including gray-headed albatross. In order to reduce the impact on the environment and to comply with ASHRAE Standard 189.1, the new building is located as close to the existing building as possible. On the north and east sides of the building, areas have been set aside for a garden containing native plants. Stormwater which falls on the site will be directed to the natural swale on the northeast of the site. In order to ensure water is used efficiently in the building, primary water end uses in the building were identified and analyzed. Showers, toilets, and laundry consume the bulk of the water used in the building. To save water, the lavatories and restrooms will be furnished with WaterSense certified low-flow faucets and shower heads. Waterless urinals will be installed in the men's restrooms and locker room. The single washing machine will be both ENERGY STAR and WaterSense certified. Building water use is also mitigated by a rainwater collection system which collects water from the roof. The system is gravity-fed, allowing gravity to do the work rather than energy-consuming pumps. A complete, small-scale water treatment facility will be installed on-site so that the collected rainwater can be made potable. In order to evaluate the effectiveness of various passive strategies, energy conservation measures, and high-performance building systems, a baseline energy model was developed. Hourly, whole building energy modeling for the project was done using Energy Plus, the industry-standard energy modeling software developed by the U.S. Department of Energy. The baseline building was built to meet minimum requirements of the owner and the requirements of ASHRAE Standard 90.1. Analysis of the baseline model showed that heating, lighting, and energy consumed by the on-site data servers were the highest end uses. Also, despite the cold climate, there were significant cooling loads. Energy consumption is fairly steady throughout the year due to the relative consistency of the climate. Building orientation was decided by considering both solar radiation and views to the outdoors. The building is rotated 15 degrees from true east-west in order to maximize heat gains from solar radiation and reduce the heating load. The living areas face the north, providing views to the ocean for the building inhabitants. Providing a healthy and welcoming living area for the meteorologists who will likely spend months at a time on the island was imperative to the CUA team. One of the most concerning issues with the existing design for the meteorological station is the lack of natural daylighting. Natural daylight can save energy by reducing the need for electric lights while providing higher quality illuminance and views to the outdoors. Skylights above the work areas and operable windows in the living areas provide natural daylight. Photosensors dim the electric lights when daylighting is sufficient, further reducing the lighting energy load. Taking into consideration the needs of the occupants, the given building was redesigned in order to provide adequate daylighting and natural ventilation. In order to accomplish our design goals without alternating the overall building footprint, a second floor was added, taking advantage of the unused double-height space on the west side of the building. With the living area moved to the second floor, additional floor area was available on the ground floor. Using this area, we created two semi-enclosed, unconditioned activity areas at the front of the building. The covered spaces give the occupants access to fresh air and exercise without having to worry about the regular rain the island receives. Structural insulated panels were selected for the primary exterior wall type due to their superior thermal insulation, ease of construction, and ease of transport to the remote island. To further enhance the performance of the SIPs, pipes containing phase change materials are embedded in the insulation layer. Phase change materials absorb and release thermal energy as they freeze and melt, allowing the SIPs to act as a thermal mass. This building is perfect for the first application of this emerging technology, as the cold but mild climate makes thermal mass a highly appropriate design strategy. On the north-facing wall in the residential area, a trome wall operates on the same principle of thermal mass. The trome wall absorbs heat during the day and slowly dissipates heat into the space at night, the time when the residential area will be occupied. Operable windows set back into the trome wall allow light and natural ventilation into the bedrooms. Three types of HVAC systems were tested in the energy model. Rooftop terminal AC units were used for the baseline as required by ASHRAE 90.1. Next, a traditional air-to-air heat pump was tested, which eliminated the cooling load and reduced the overall energy used by 15%. Then, a variable refrigerant flow system with a dedicated outdoor air system for ventilation was tested, which reduced the overall energy used by 48%. When an energy recovery ventilator was added to the VRF with DOA system, the overall load was reduced 55% from the baseline. In the final system layout, the data server room is supplied by the DOAS with 100% outdoor air, significantly reducing the cooling load. The return air from the data server room is used to preheat the outdoor air for the remainder of the building through the energy recovery ventilator. The remainder of the heating and cooling loads are handled by the VRF system. As lighting accounted for 20% of overall energy used in the baseline model, providing the most efficient lighting possible was critical. Therefore, all electric lighting in the building will use LEDs. Plug loads were optimized by selecting efficient Energy Star rated products. Smart plugs will be installed which disconnect unnecessary receptacles based on occupancy. The data server types were specified in the owner's requirements, so the load could not be reduced. Several types of renewable energy were considered to provide for the remaining energy loads. A flat plate solar hot water system with 4 collectors will meet the domestic hot water demand for about half the year during the summer. A larger system was not selected because of the low solar radiation level during the winter. PV analysis showed that PV production on site is not adequately efficient to count toward the renewable energy requirements of ASHRAE 189.1. However, as a donor pledged the funds to provide a PV array which covers 5% of the total building energy needs, a system which closely meets that load will be installed. Wind energy proved to be the most productive renewable energy source for the site. The average annual wind speed is 20.1 miles per hour. 2 50-kilowatt rated wind turbines will be installed on site, providing for almost 85% of the total building energy load. The EUI of the redesigned building is 58 kilobtu per year. An EUI of 30 is generally considered net zero capable. Still, the building comes very close to achieving net zero because of the high output of the on-site wind turbines. Noise can be a source of discomfort for building occupants. Therefore, the walls which surround the equipment rooms and service stalls are designed to reduce sound transmission to the surrounding spaces. The walls use a staggered stud design which isolates sound to one side of the wall. Another way the indoor environmental quality will be improved is through the use of living walls. Living walls have all the benefits of green walls, such as improved occupant productivity, carbon reduction, and aesthetic value. They differ from traditional green walls by using fans to force air circulation through the growing medium, increasing the IAQ benefits. Thermal comfort analysis was completed to ensure that the indoor environment meets ASHRAE Standard 55. The unmet hours were calculated within the energy model. The total energy annual hours where the thermostat set point is not met is 24.25. Less than 300 is considered acceptable. Planning for waste management during construction and during building occupancy helps to reduce the cost for wasted materials and reduce the impact on the environment. We plan to reuse the material from the existing building on the island, which will be carefully deconstructed. A building management system with the capability to control the HVAC, electric, plumbing, and renewable systems will be installed prior to inhabitation. The system will ensure the building is operating at maximum efficiency and allow for post-occupancy analysis of actual energy consumption. The initial cost of the proposed building is slightly less than twice the cost of the baseline building. However, life cycle cost analysis shows that the improved building will pay for itself in 8.5 years. Over the 50-year expected life of the building, there will be a total savings of more than $5 million. The new meteorological station, as designed by the CUA team, will provide superior energy performance and lifetime cost saving to the building owners, while providing a healthy and comfortable living and working environment to the meteorologists, who will call the building their part-time home.